went into power saver mode. So there we go. Draw. Okay, so let's see. Yeah, so let's come up, I think, like properties of capacitors. Properties of capacitors. So we got an intro, huh? And something like we report on our exploration or determination of a device called a capacitor. So we will describe its no apostrophe, its basic properties, its basic construction, and the equation that describes it. Describes it. What else? And then we will then show I don't know exactly yet. Rules of combination. What else? There is the rules of combination. So we're going to and then what else are we gonna? Rules of combination, and we'll also explore the time properties, something like that. Okay, so you have that the parallel plate model. So then you have we have two parallel plates and then there's an equation, and there's actually two equations. And so you can relate the model to these equations. Remember, area and Q are pretty easy to understand. And then the distance and voltage because of E fields. So you say that we postulate that energy is stored in the E field. Postulate just means we say without proof, because we're not writing a book here. We're just writing a couple of pages of report. Stored in E field. And so you could say, look, if we have a battery and we have a capacitor, and so there's a certain amount of Q, for example, this has some voltage, that kind of thing. And you can also say, one should note, or we observed, or we concluded by observing the model capacitors won't conduct steady state current, right? We talked about this. They fill up with charge. And we said it today that when they fill up with charge, they develop their own voltage, won't conduct steady state current because you need that later on. And if you accept the model, then that's got to be true, right? And report. I'll go back. I hopefully people aren't freaking out on me there. Okay, then the rules of combination. So you say, let's think about it. So first of all, we can imagine C1, C2. Oops. Well, okay, we have a battery. So this is series, and the rules of series. So a series circuit um, um, says that delta V C1 plus delta V C2 has to equal V battery. So this implies that, and we have the basic equation. So V equals, what was it? Q over C. So this implies Q1 over C1 plus Q1, 2 over C2 equals Q over C total. And you say, but Q1 equals Q2 equals Q total. And so this, then we end up with Q times 1 over C1. So I want to keep this really short. We're not going to go through that whole long explanation that we did the other day because we don't need it. We're just showing that we're exploiting these, we just simply say we're exploiting the rules of series circuits. That's it. And the rules, one of the rules of series circuit is that the two capacitors or the two circuit elements here, the voltage across each of them has to equal the battery voltage. Excuse me. Okay. Then that's series. And then we have parallel. And so excuse me, the parallel is then, what was it? It was, oh yeah, IC1 plus IC2 has to equal I total. I'm not going to write every blessed thing out of here. And so, oh, wait a minute. Sorry. There is no I's in capacitors. I'm thinking of resistors. And so, what did we say? Oh, yeah. Right. Just give me a minute. So we have, once again, Q over C, V equals Q over C. So it's C1, Q1, C2, Q2, and there's some kind of Q total. So what we said is that, oh yeah, so, right, so the parallel plate, you can, I didn't say this the other day, but the justification of this is that there's nothing wrong with just saying now this one has area 1 plus area 2. I mean, not plus, this is area 2. So this is area 1 plus area 2, which of course tells us, oh, since Q, we have Q over V equals V over D. If we, oh, what did I do? Give me a minute. Give me a minute. Area. So if we increase the Q, yeah, right. So we say, gotta keep it simple. Keep it simple. Right. So if we have epsilon 0 A1 over D, the same D, because it's the same V, plus epsilon 0 A2 over D, it's also going to equal Q1 over V. I didn't do this last time. I just thought of it. Q2 over V. So everybody is the same. So this implies that epsilon 0 A total over D equals epsilon Q total over D, and since A total, this can be done better. I'm just making this up quickly, and now we see how Q total equals, yeah. So for the point of a report, you just say in the parallel combination, Q total equals Q1 plus Q2. And so this lets us do, so again, so C equals Q over V. So Q equals CV. So C total, V equals C1 V plus C2 V. And because the V's again, C total V equals V C1 plus C2, because it's all the same voltage. Parallel, so that says V bat equals V C1 equals V C2, right? So again, this whole derivation here should go in your notebook. You don't want to write all that out in a report. And then, well, wait a minute. We're running out of time anyway, damn it. I have to make this a recording and so people can look at this offline. And I just eventually have this posted in Canvas, how to do the report. Okay, so then, oh yeah, then the time properties. And remember, I gave you all those notes earlier. So we expect the charging to look like this and the discharging to look like this. So V as time equals V bat. So this is the discharge. So minus T over RC. So we expect this behavior. So when in procedure, then you, and we have this from last week, you describe the test rig. And with the known C and the DUT, and this, and so this depends on the series combination rule to be, it has to be correct. It depends on the series combination rule. So we first need to measure two known C's, C1 and C2, and show that we can get the correct answer. And then we then measure the series and parallel combinations, and then compare to prediction. And then you need to then talk about the exact not step by step by step. You just say, look, we set up this circuit and we press the button to take a measurement of the voltage. So you had two challenges. The voltmeter reading decayed. So you took 3 measurements and you noticed that you needed to, we needed to add the Z switches, needed to add Z switches. And so you don't have to go through a long explanation of the steps you took. You just say that in between each measurement, we had to make sure each capacitor was at 0 Q. So you need to mention something about, it depends on its a series combination rule of the device, but it also depends. In fact, all the calculations depend on Q of the cap to start at 0. We always, whenever we take any of the measurements, we assume that the cap started at 0 Q. When it comes to the time measurement, it takes care of itself because we charge and we discharge it through the voltmeter. And then the time measurement, we've already been through it.
Professor, can you go back?
Oh, I'm sorry.
Just for like 5 seconds.
Of
no,
course.
You're good. Thank you.
Sorry. Great, thanks. Okay, then the time measurement, we've already been through it, so you have plenty of notes. You just show you can show the circuit we set up. Let's see the battery, and we had the switch, and we had the voltmeter. So we did we needed first our voltmeter. Whoops. And we got that from measuring T1/2 using this equation. And then we plotted, next we plotted V as a function of time alongside the equation V equals V bat e to the minus t over RC. And these are the, for example, that's our voltmeter, huh? And then you say, all right, well, just say some word. And then next step, of course, is the data tables and a quick and an explanation of what's in the, explain them. By now, most of the equations have been written out anyway, and so you can just say this box uses equation 1. This box uses equation 2. And then right. So I've already talked to you about how to do there's a few statements about the if you've demonstrated or not. And there's look in the lab manual, and just in case, look for questions in the lab manual. I don't think, let me double check. I don't think there's anything in here particularly special. No, there aren't any questions this week. Yep. Okay, good. There's there are different ways of deriving, and I don't like the way they do the derivations, so I did my own. There are no questions. Okay. All right. So what do we got now? We have 25 minutes. Any questions? I will publish these notes tomorrow at some point, and I will try to make a separate recording of this report outline.
Professor?
Yo.
It says we needed first. What's that next word?
Okay, we needed first. Our voltmeter.
Oh, thank you.
Yeah, I was going too fast. I want to avoid erasing too, because I don't want you guys erasing in your manuals. Using this equation and this technique. And this circuit. And then we applied V as a function of T. We took a table of times and voltages. Oops, that was like this. And this is, right, this is a discharge measurement. Discharge. And then we also plotted the function. And qualitatively, meaning that we didn't do a chi-square or anything. I mean, we didn't do a fit or a residual squared, but it seems like we would claim that the equation is verified. Which I suppose goes into the, we would claim this is in the analysis / results conclusion. So you're saying the rules of combination are correct because of this data, and because our percent difference is so tiny. The equation of the voltage as a function of time, we can't prove it. We don't have like a residual squared fit, or we don't have a percent error. But if one looks at the diagram, the line just follows the data so nicely, for sure, that we feel very confident that we could prove this equation is true. Something like that. Oh boy. So any questions? Because I want to, we're falling behind, and I had hoped to get DC circuits started. So I'm going to ask you guys, there's no pre-lab assignment for next week, and I'm going to ask you guys to fill in a data table on your own time other than class time so we can get through next week. Okay, so if there's no question on this, I'm going to stop and restart the recording to make it a little bit easier for me to break this up.